Hello dear students, today I will discuss about gradient, divergence and curl, that is depend on vector function, vector point function, scalar point function. Okay, so here scalar and vector point functions. What are the point function? Point function means whenever we consider a 3D space, suppose there is a point, if corresponding to each point we can get a variable quantity, we can get a value of a variable quantity as a scalar, then we can say that that is scalar point function corresponding to each point. If in a space there is a point, suppose in 3D space there is a point, suppose P, okay, and its position vector, its position vector is R. We can write like this: point, there will be origin, so this is position vector of this point. In 3D space, if there is a point having position vector R, and also in the case of rectangular coordinate system, we can suppose its coordinate as what? P, X, Y, Z. If rectangular coordinate is X, Y, Z, then we know in 3D vector R equals to Xi plus Yj plus Zk. This is the position vector of this point. Okay. Corresponding to point in a region, in a space, suppose there is a point corresponding to this point, we can get a scalar value. And suppose point varies in a region, in a space, then for that reason, if we can get scalar value corresponding to each point of that region, then we can say that is the scalar point function. Just like function of x, function of y, function of x means function of variable x, the function of point. So we can suppose function phi. This is depend, the value of this depend on the point P. So if to each point P, maybe x, y, z, maybe PR, this P, we can get a value of a variable quantity phi, a unique value, and that is called scalar point function. If we get a scalar point, so a scalar point function, it can be written also represent function of R. It can be also written like this: x, y, z. This is in vector notation. This is in rectangular Cartesian coordinate notation. Triplet as a point. Point having this coordinate, point having this position vector. So these are the what? Scalar point function. Depends on the point in a region of the space. Okay, so scalar point function. Just like this is what we can write in terms of x, y, z, I, j, k, and it position can depend on a parameter just like temperature at some particular value of T, that is value of, at a particular temperature, the point is here, and then in another place the temperature may be different, T maybe. So at that point, x, y, z will be different value, vary as distributed places. Okay, so phi x, y, z is what? A scalar point function. Okay, for example, temperature distribution in a heated body, temperature, and also density of a body. Okay, potential under gravitational force, all are the scalar point function. So a scalar point function is a function of three variable in a space, we can suppose. Okay, so we can also use for a small f, but phi generally used for a scalar point function. Okay, so we can write like this also, f of this r, you can use small f. Okay, f of x, y, z, etc. So there is a scalar point function, a scalar point function, a scalar point function, a scalar, a scalar having no direction. Okay, now similar type of definition we can give for vector point function. If corresponding to each point of a region in a space, we can get a vector quantity. We can get a vector quantity, unique vector quantity, then that is called vector point function, because depend on the point. So vector point function is generally denoted by like this, f of, then this will be called vector point function if we can get a vector. Okay, for vector point function just we use symbol, bold symbol. Vector point function means that just like for a scalar point function, its value may be x, y, z, and vector point function means what? Maybe its value with I, j, and k, because that is a vector quantity we can get. Okay, so we can write also like this, x, y, z, vector quantity, vector, that will be what? Vector, vector related, just like this, x square I, y square z plus z square k, it may be vector point function. If corresponding to each point of a region of a space, we can get a unique vector quantity, then that is called vector point function. So first vector point function is also dependent on the point, but corresponding to each point we can get a vector quantity, that is vector point function. Okay, so vector point function, vector point function was point dependent. Okay, vector point function, generally we are requiring this value r, that is point having this position vector, point having this rectangular coordinate, point having this position vector, that is denoted like this, x, y, z. Okay, so this is point function, vector point function and scalar point function. They are very very important for solving questions, because for divergence, gradient, curl, directional derivatives we are using function. For gradient and directional derivative, we will use scalar point function. Now, a scalar point function means what? Function of three variables x, y, z. Okay. So function of three variable, we know about function of three variable. Function of three variable means phi x, y, z. Function of three variable. Okay. So suppose value of this function is equals to a constant c, a constant, a constant. Then corresponding to the value of c, suppose c equal to 1. If c equal to 1, then phi x, y, z equals to 1. C equals to 1. Phi x, y, z 2. C equals to 2. So in this case, when c equals to 1, so value of the function is 1. Always. For all values of x, y, z. So, and we know that the three variable function represent a surface in a space. So, if this surface, in this particular surface, where this is 1, so phi x, y, z equals to 1, this is surface. If this surface passing through a point, suppose this surface passing through a point P, and this surface is passing through point P, and here for all x, y, z, that is for all point, the value of the function on this surface are same. Similarly, in this surface also value of the function is 2 always. So this type of surface is called level surface. Level surface. Level surface of phi. Level surface of phi. X, y, z passing through P. Clear? Phi x, y, z equals to constant is level surface of phi passing through P. Through a point P, if we draw a surface in such a way that on that surface the value of the function remains same, then that surface is called level surface. Okay? So, two level surface cannot intersect. Why? Because if we draw, because here on this surface the value of the function is same as 1, and on the another level surface, on that the value of the function is 2. Then whole surface, the value of the function is 2, this level surface passing through the point P. So in this level surface, value of the function is what? 2. Here phi equals to 2. Here phi equals to 1. This two surface cannot intersect, because if intersect, then value of the function phi equal to phi, at all the point the value of the function is same, that will disagree with, because here phi equal to 1, here phi equal to 2, so two level surface cannot intersect. Okay, so level surface means the value of the function or on the surface are same on the whole surface. Okay, so through a point we can draw a level surface. Now, main thing is that for this three quantity, gradient, divergence and curl, there is a vector differential operator. That is very, very important, and using that operator we will define gradient, divergence and curl. So first of all, what is vector differential operator? So see here that vector differential operator. Operator, differential operator, we know what? dy dx, del y del x. So in 3D space, del y del x, del y del y and del y del z. This is differential operator. Partial derivative with respect to s, with respect to y, with respect to z, and just unit vector I, j and k. This combination, vector differential operator, I del y del x plus j del y del y plus k del y del z. This is a operator. This is a operator. Just like dy dx, differential operator. This is vector operator. Vector differential operator. Why? Because this is differential operator, this is differential operator, this is differential operator, and also I, j, k are vector. So vector differential operator. This is operator operate on a function, maybe scalar point function, maybe vector point function. So first of all, if phi x y z or scalar point function phi x y z, then we can apply on this. We can apply on this. This operator can be applied on the vector point, scalar point function phi. So first of all, note down this is denoted by del. This is denoted by this. This is del, called del or nebula. Okay. So del operator. This is denoted by del. So this is our vector differential operator. Okay. This is denoted by del and this. Vector differential operator. Vector differential operator. That is denoted by del. Now if phi xyz, phi xyz equals to C is a level surface, or not level surface, here we can say that if this be a scalar function, scalar point function, scalar point function, if phi xyz be a scalar point function, phi xyz a scalar point function, be a scalar point function, then just apply this operator on that function. Okay, del phi, del phi. Operate this on this. That is, del means I del y del x plus j del y del y plus k del y del z. This is operator and this is the function phi. This I del phi by del x plus j del y del y del phi by del y k del phi by del z means phi will go to this place. here. Operator, differential operator. This is a vector. This is a vector. Okay. This is a vector. And it is known as gradient. Okay. So this is called what? Gradient of the scalar point function, which is called the gradient which is called the gradient of a scalar point function. A scalar point function. Gradient of a scalar point function. That is gradient of a scalar point function. Okay. So gradient of a scalar point function phi. This is very important quantity, gradient phi. Scalar point function, whenever we apply del operator, that is del operator, this vector differential operator is applied on a scalar point function, then we get a vector quantity because ijk is there. That means this is vector. This function of xyz, function of xyz, function of xyz. So this is gradient of phi. Also, we can write thus gradient phi. That is notation of gradient of scalar valued function. Gradient phi, grad phi is equals to del phi equals to this sum of I del phi by del x. We can also write in short because here there are I, j, k. So phi x, y, z function. So x, y, z summation over I, j, k. Okay. I del phi by del x plus del. That means what? In short, we can write it. I del phi by del x, j del phi by del y, k del phi by del z. This quantity can be written in short like this, sum I del phi by del x in short. This is gradient divergence, gradient del phi, sum of this. So gradient phi can be written like this. Okay. So definition of gradient. Gradient is a vector quantity. Here, grad phi. Okay, del phi. Now, we will understand what is the geometrical meaning of this gradient. Very important topic. Okay, so now we know what is vector differential operator and also gradient phi. Gradient means del operator applied on scalar point function, and vector quantity means having direction and magnitude. Okay, now just we want to see what is the direction of del phi and what is the magnitude of del phi. What is del phi? Del phi means gradient phi. Now geometrical meaning of gradient phi. We want to No. Okay. So for that, just in the previous definition we see gradient means del phi. Del phi is a vector quantity. So its direction and its magnitude both can be find. So here phi xyz represents a surface, and we know level surface. Level surface means the value of the function on the surface remains same. Okay. So geometrical meaning of gradient. Grade phi. Geometrical meaning of grade phi means del phi. Just in the previous section I give the definition of grade phi, that is what? Del phi. What? Sum of I del phi by del x. Grade phi. Geometrical meaning we want to know. Okay, for that, so very we will understand in very short by using the diagram. Suppose this is a level surface, phi equals to c. Phi means xyz, function of xyz, phi means. And this is another level surface, phi plus delta phi. Phi plus delta phi equals to c1. Okay, we can write constant, any of the constant. So this is a level surface, this is a level surface. Now here suppose here is a point P. Here is a point P. Its position vector is R, and here is a point Q. Its position vector R plus delta R. Clear? And this is what? Delta R. And suppose perpendicular distance between these two level surface, this is level surface, this is level surface, on phi xyz is our scalar function, phi xyz, phi, where phi is function of x, y, z. Now phi x, y, z equals to taking this constant level surface corresponding to another level surface, there constant will be different, phi plus del phi. The value of function will different, so phi plus del phi, difference is del phi. So here phi plus del phi equals to constant. So this is a point on this level surface, this is a point on this level surface. Now suppose perpendicular distance between these two surfaces, perpendicular distance is this. R. Perpendicular distance is this. In this perpendicular direction, this is the perpendicular distance, and this distance is, suppose, delta m. This distance is delta r. Now, in this direction, if unit vector we take, and also in this direction unit vector we take, suppose we take in this direction unit vector n cap is the unit vector in this direction, and in this direction unit vector, suppose in this direction unit vector is n dash cap. N dash cap is unit vector in this direction. Okay. Now, here this is PQ is what? Delta R vector. This vector. Position vector of R, position vector R plus delta R, this is delta R. Okay. Now, here del phi is equals to what? I del phi by del x, j del phi by del y, k del phi by del z, and vector delta r, this vector. Okay, vector delta r in this direction. Vector delta r is what? I delta x plus j delta y plus k delta z. Here, when we take limit delta tending to d, so we can also write it as a d, as a limiting condition. So here see, del phi equal to this, delta r equal to this. We see that del phi, that is get phi, dot product, vector quantity, and delta r. If we take dot product of these two, then we get del phi by del x dx. Dx, delta x, we can write as delta x plus del phi by del y delta y plus del phi by del z delta z. It can be written as delta phi. As in the limiting case, you can write this is d phi, total differential. This what? Del phi dot delta r is equal to this we get. Okay? This. Now from here we see that if or on the level surface, we can write del as also d. When it take limit, this point tending limit as this point lying on this level surface, that is q tending to p. In that case, we can write delta to d. So here just write delta. So on the level surface, phi xyz equals to c phi xyz equals to c delta phi equals to 0. And as if q tends to just here on this level surface, if q lies on the level surface phi xyz equals to c, then delta phi tending to d phi is equals to 0. Delta phi tending to d phi and also d phi equals to 0, delta phi equals to also 0 you can consider, because q lies on this, just limiting case take, then delta r tending to d phi and d phi equals to 0. So here we can use also dx dy dz, this tending to this tending to 0, delta phi tending to 0. Okay, and so we get delta phi tending to d phi equals to 0, delta phi equals to 0, del phi dot d phi is equals to 0, not d phi, dr equals to 0. Okay, r vector dr vector equals to 0. Dot product of two vector equal to 0, that means they are perpendicular to each other. So implies del phi is perpendicular to dr. Del phi is perpendicular to dr. Okay, q lies on this then, and when q lies on this, that means delta tending to 0. So delta tending to 0, that is delta phi tending to d phi also, and here delta phi will also 0 when q lie on the level surface phi equals to c. So delta phi is perpendicular to dr. Dr means what? This dr tending to delta are tending to dr. On this delta r is lie on the level surface phi equals to c, and as q lie on this surface, delta phi equals to 0. That is q tending to p, and this is a line to the surface phi equals to c at p. Okay. So here we see that del phi is perpendicular to every line to the surface at P. So This relation is important. Okay. So here we can say after this line we can write as Q lies as if Q lies on phi equals to C, then delta phi is equals to 0. Delta phi equals to 0 and delta r tending to dr. So del phi dot dr equals to 0 implies that what? This equal to 0 implies that del phi is perpendicular to the every line dr perpendicular to the every line dr to the surface at the point P. Del phi is perpendicular to the every line dr. Here, this is tending to here, then line will be this, like this. So, del phi is perpendicular to every line dr to the surface at the point P, which implies that del phi is in the direction of normal to the surface at P. Surface at P. Just you can write here surface phi x y z equals to C at P. Means direction of phi, del phi. Del phi is in the direction of normal to the surface phi equals to C at P. That is direction of del phi is in the direction of normal to the surface. Normal means here, that is here dr is tangent to phi equals to c at P. So every line that is tangent plane, so del phi is perpendicular to that plane, the perpendicular to this line, every line at the point P to the surface A, phi equals to C. So del phi is in the direction of normal to the surface phi x y z equal to C at P. That is, here dr is tangent to phi equals to C. Okay, so gradient phi is a vector whose direction is in the direction of normal to the surface at that point. Okay, now magnitude. For magnitude, we will solve here we get direction of gradient phi. Now, direction of gradient phi is what? Along the normal to the surface at the point P. So we can write gradient phi is a vector whose direction is in the direction of normal to the surface. Okay, here see, therefore we can write del phi equals to power of del phi n cap. N cap is perpendicular to the surface at P, phi equals to C. So this any vector is equals to what? Modulus of that vector and unit vector in that direction, in the direction of the vector. So del phi equals to this. Now we want to find the value of this. Okay. Now, if delta n, this is delta n, is the distance between these two pair. Now, perpendicular distance between two level surface says B delta n if perpendicular distance between two level surfaces be n, this is the perpendicular distance between two level surface. This is perpendicular distance between two level surface delta n, and its distance is what? Delta r. Okay, so then rate of change of phi here, just see, del by del x dy dx means what? Dy by dx. We know the rate of change of y with respect to x in the direction of x. X is in which direction? Here we take direction in this direction. Suppose in this distance is delta n. Then delta phi upon delta n ratio tending to what? Del phi by del n. What is this? When q lies on this surface, there is tending value, delta tending to 0. At that case, delta n also tending to 0. So, del phi by del n, that is partial derivative. Del phi by del n, this is what? Rate of change of phi. Rate of change of phi, because this is phi. And in this direction, the rate of change, in this direction, phi will increase. So, del phi by del n. Del phi by del n means rate of change of phi in this direction. Delta n in this direction. So, rate of change of phi in the direction of normal to the surface at P. Because normal, this is the normal direction. Okay. Then, the rate of change of phi in the direction of normal to the surface, phi equals to C at the point P is given by del phi by del n equals to what? Limit delta n tending to 0, delta phi upon delta n. Delta n is distance. Delta n tending to 0. Delta r tending to 0 and delta n tending to 0 when q lies on P. This is limiting condition. So del phi by del n equals to limit delta n tending to del phi by delta phi by delta n. Now delta phi by delta n, here we know delta phi equals to what? Delta phi equals to limit delta n tending to 0. Here del phi dot delta r upon delta n. Because you know there are very important relation what? Since delta r equals to del phi dot delta r. Delta phi equals to del phi dot delta r, we know. So del phi dot delta r. Clear? Now, from here we can say that del phi equals to mod del phi, mod magnitude of this, into n cap. So we can use here. Okay? So from here we can see that so from here we see that del phi by del n equals to limit delta n tending to 0, del phi equals to what? Mod of del phi n cap. Its modulus is this, and n cap in this direction dot delta r. Clear? Upon delta n. Yes? Now, here delta phi modulus can be written outside. Now limit delta n tending to 0 n cap dot delta r vector upon delta n. This is. Now see here in the diagram, if this is angle theta, suppose, and this is perpendicular. This is delta n, this is delta r. Its value delta r, distance. Okay. From here, in this direction, n cap. In this direction, n dash cap. So here, n cap in this direction. Delta r in this direction. Clear? This is theta. So we can write dot product n cap that del r, n cap dot delta r equals to n cap dot delta r equals to what? Modulus of n cap, modulus of delta r, cos of theta. In this direction, in this diagram. This is equals to what? 1 dot delta r cos theta. Modulus delta r, that is delta r cos theta. Now in this diagram, delta r cos theta equals to base by hypotenuse. This is delta r, delta n, delta n by delta r. Cos theta equals to delta n by delta r. So delta n by delta r equals to delta n. So this is equals to delta n. Delta n. So mod del phi limit delta n upon delta n equals to mod del phi implies so this is modulus implies magnitude of del phi. Magnitude of del phi is the rate of change of phi in the direction of normal to phi equals to c. Rate of change of phi in the direction of normal to the surface. This is magnitude of this. Okay, so finally we get what? This is a vector. So finally, geometrical meaning. What we can write? Final, we get gradient phi, that is del phi is a vector in the is a vector normal to the surface. Normal to the surface, phi equals to c. Gradient phi del phi is a vector normal to the surface, phi equals to c, and this gives direction normal to the surface. Is a vector along normal to the surface, phi equal to c, and its magnitude is the rate of change of phi along this normal. Rate of change of phi along this normal. Okay, magnitude equal to the rate of change of phi along this normal. Magnitude is equal. You can write equal to, its magnitude is equal to the rate of change of phi along this normal. This is geometrical meaning. This is geometrical meaning of gradient phi. Okay, so very important this thing. What? Magnitude, rate of change of phi along this along the normal to the surface, and magnitude direction normal to the surface. Okay, and here we can see another thing, that directional derivative. So second thing is what? Directional derivative. What is directional derivative? Derivative we know, derivative dy by dx, derivative differentiation of y with respect to x, derivative of y with respect to x. So derivative here also del phi by del x, that is derivative, partial derivative of phi with respect to x along the x axis, along y axis, along z axis. Del phi by del x, del phi by del y, del phi by del z means what? Del phi by del x, del phi by del y, del phi by del z means partial derivatives along x axis, y axis, z axis, in the direction of x, in the direction of x axis, in the direction of y axis, and so on. Okay, so here directional derivative. Suppose this is level surface and phi increase in this direction, and from here, from this points on the surface there is a point. From this point in any direction we can find derivatives. Suppose this is the direction, n cap direction, n cap, n dash cap. You can write n cap direction. Okay, suppose n cap is direction. In this direction, maybe any direction. In any direction, we can find derivative of phi. Okay. So, if delta is the distance, this is the distance, delta distance. Delta is distance along this direction. Suppose in the given direction, this is a given direction. Suppose for sometimes, suppose this direction is a cap. In this direction, unit vector is a cap. Now in this direction, suppose this is the length delta r. Delta r is the distance. Okay, in this direction. Now, when we suppose Q lie on this level surface, in that case delta tending to 0. So the limiting position for changes in phi, that is delta phi by delta r. When Q lie on the surface phi, that is delta tending to 0. So delta tending to 0. So limiting position. This is known as derivative of phi along the direction a cap. That is delta phi upon delta r. Directional derivative along the direction PQ. Directional derivative along PQ is along PQ. This is the distance. Okay. So here we can write thus. And also in a direction, we know del phi gradient. This is a vector. Its component in a direction we can find. Suppose in the direction of a vector. Suppose a vector, there is a vector a. In the direction of this vector. Direction of this vector is what? A cap, unit vector. So in this direction, if we find its component, this is the component of this vector in this direction. Direction is in the direction of the vector A. This is called directional derivative along the vector B. That is, we can say that directional derivative of phi directional derivative of phi is the resolved part of del phi in the given direction. Result part of phi in the given direction. Directional derivative of phi is the result part of del phi in the direction in the given direction a cap. That is gradient phi dot a cap. Okay, and in the limiting case, we can write del phi by del n limit r, del r, delta r tending to 0, delta phi upon delta r. Delta r is what? This distance in the direction of a cap. Clear? And delta phi, this. Well, here is the point, is that in this direction, up in this direction, in the distance of this, the value of phi is increased by delta phi. That is the delta phi. Okay, so increasing part is of delta phi. So delta phi by delta r. Its limiting value is this. This is the directional derivative. In the limiting case, we can write directional derivative of phi is equals to this. Directional derivative of phi is equals to del phi by del r equals to this. Now this can be written as in this form. We can say from here by derivation. How? This is delta n, this is delta r. So from here we can say that from this position cos theta, since cos theta equals to what? Delta n by delta r. Okay, so this implies delta r equals to delta n upon cos theta and n cap dot a cap equals to and n cap dot a cap equals to 1 dot cos of theta. Okay, so implies delta r equals to delta n upon n cap dot a cap. Okay, so here limit delta r tending to 0 delta phi upon delta n upon n cap dot a cap. This, that means limit delta r tending to 0 n cap dot a cap delta phi upon delta n. Now in the limiting position, delta tending to 0, that means delta n tending to 0. So n cap, a cap, it can be commutative, so we can write a cap dot n cap here limit delta n tending to 0 as delta r tending to 0 delta n tending to 0. So delta n tending to 0 delta phi by delta n. This is del phi by del. So you can write a cap dot n cap del phi by del n. This is del phi by del n by limiting position. So this total can be taken. This is what? Gradient phi, del phi. So this is equals to del phi. So you can write a cap dot del phi. This is del phi. This is del phi. Since del phi equals to what? Del phi equals to del phi by del n into n cap here. This is the reason. Del phi by del n into n cap. This is del phi. So a cap del phi. Commutative, so you can write also a cap dot grade phi. Okay. That is a cap dot grade phi. You can also write like this. Okay, so this is the derivation. Del phi by del r equals to a cap dot del phi. A cap dot del phi. Del phi can be also written as grade phi. A cap dot grade phi. So very important formula is this. Okay, so del phi by del r directional derivative. Along the direction, what? A cap is a cap dot grade phi. A cap dot del. That is our formula is what? Directional derivative of phi is del phi by del r equals to a cap dot grade phi or a cap dot del phi. Very important formula. Directional derivative dt. Directional derivative dt. Directional derivative, okay, of phi is del phi by del r a cap dot grade phi. A cap dot grade phi along a cap. Clear? So remember this formula, very important formula. Okay, by using this we have to find directional derivative, and also this formula is very important. This is del phi by del n is modulus of grade phi. Okay, and from here we see that if this angle is 0, So here we see that this is the value of directional derivative. Just see one more important result is here, that del phi by del r. Okay, so take del phi by del r equals to this theta. We know del phi is along this direction, and in this direction a cap direction is this. So here this is equals to what? A cap modulus del phi cos of theta. So we know this is equals to 1, this is mod del phi cos theta. Now this is less than equal mod del phi, as cos theta is less than equal 1. Cos theta is less than equal 1. So this is less than equal 1. So del phi by del r, directional derivative del phi by del r is less than equal del phi. That is the directional derivative. The maximum value of directional derivative is mod del phi. Maximum del phi gives maximum directional derivative, because for getting maximum value cos theta equals to 1. So if theta equals to 0, then this direction is along this direction, that is normal direction. So maximum directional derivative is along the normal direction. Okay, so if theta equal to 0, then del phi by del r is equals to del phi by del r equals to what? Mod del phi. That is maximum value of directional derivative is the maximum value of directional derivative is along the normal direction. Along the normal direction. And is given by del phi, and is given by del phi modulus. Okay, here this maximum value of directional derivative is along the normal direction and is given by mod del phi. So del phi gives the maximum directional derivative. Okay, so these are the very important formula. By using this formula we have to solve some questions now. Okay, take a question first, that is, prove that we have to show that del r to the power n equals to n r to the power n minus 2 vector r, where vector r equals to xi plus yj plus zk. So very simple questions here. Del means you know del operator. What del operator is? Del equals to I del y del x j del y del y k del y del z. This is an operator. Okay, and always remember that very simple, either this vector or this vector. Generally we are denoting capital R or small r. Okay, this is a arbitrary point having coordinate x y z. Point having coordinate x y z. You can write also position vector op equals to vector r, position vector. Okay, that means r equals to what? Xi yj zk. Okay, and its modulus r or modulus r is equals to small r. Okay, that is a small r, and we know a small r modulus is given by root over x square plus y square plus z square. So remember this relation, very very important relation, always useful. Okay, so here r square equals to x square plus y square plus z square. For solving questions, this is very very important. It is general, as usual we use this notation. Okay, so here r square equals to this, means r is a function of x, so del r by del x we can differentiate it, del r by del x with respect to x. So what we will get here? 2r del r by del x, 2x. So we can write del r upon del x equals to x by r. So very very important. So we will similarly del r by del y equals to y by r. Del r by del z equals to z by r. Okay, so these are the important part. As usual we use always this. So here for proving this, as usual r equals to this. So del phi, just we know del phi means implies how del operate on a scalar valued function. Here a scalar point function. This is r is a function of what? R is a function of x y z. In place of phi we can suppose Rn, because this is function of xy. Here del phi is what? Del phi I del phi by del x, z del phi by del y plus k del phi by del z. So this is our formula for finding gradient phi del phi. So here r del of this phi, r to the power n equals to what? X square plus y square plus z square power n by 2 we can write, since this is equals to what? Phi x y z. Therefore del of r to the power n equals to, that is del of this phi, that is I del by del x plus z del by del y plus k del by del z. This is operator del, and phi in place of phi this x square y square z square power n by 2. Clear? Now we can solve it. Equals to I del by del x square plus y square plus z square power n by 2 plus this and this. Both what? with I, with Z, with K. So same thing with respect to X, with respect to Y, with respect to Z. We can write I. What will be the value of this? N by 2 x square plus y square plus z square, or n by 2 minus 1 into 2x. N by 2 x square plus y square plus z square power n by 2 minus 1 and x square 2x. This will be the value plus z k. Same type of value you can get. Okay, z k with respect to y, what? Del phi by del y, del phi by del z. Phi means what? This as a similar part. So here see what we get. I 2 cancel x, nx, nx, I, nx, x, 2 cancel, and x square plus y square plus z square equals to r square. This r square. So power r square, power 2 cancel. So r to the power r square power n by 2 minus 1 plus ix n r to the power n minus 2 plus z n zy. Similarly, we can write its value similarly because as symmetric x, y, z. So here x, here y, and n r to the power n minus 2 plus k z n r to the power n minus 2 k z I. So here take common r to the power n minus 2. Take r to the power n minus 2 common, and we get xi, yj, zk. This is what? R. So n r to the power n minus 2 okay, so this is the result. N r to the power n minus 2 vector r. N r to the power n minus 2 vector r. So here similar process, del phi by del x, del phi by del y, del phi by. This is del phi by del x. Just as a similar fashion. Here x, just here y, here z. So we can write similarly. Similarly. Okay. So this is the result. Okay. Now take second question. Find the angle between two surfaces, this and this, at the point 2 minus 1, 2. Angle between two surfaces intersect at any point. Then the angle between two surfaces at that point can be found by using the angle between their normals at that point. Because if whenever curve or surface intersect at a point, then at that point angle between two surface or curve are given by the angle between their normals at that point. Okay, normal means perpendicular line to the tangent. So here we know gradient, that is del phi, is along the normal to the surface. So suppose at at the specified point we find the gradient or del phi, then we can get normal at that point to the surface. So after finding normals up to surface at that point, we can find the angle between two surface at that point. So very simple, just find del phi 1, del phi 2. Here first surface phi 1, second surface phi 2. That is the main technique for finding angle. So here given just like this, suppose this is curve, this is curve, at this point this is a tangent line, this is tangent line. Here perpendicular line is this, here perpendicular line is this. So this is the angle N1 and 2. Clear? Whenever this is phi 1, this phi 2 to surface intersect here, now normal to this del phi 1, that is del phi 1, this is del phi 2. Now angle between these two vector, we can see that what? Cos theta equals to N1 dot N2 upon N1 modulus N2 modulus. We can find angle. So first of all, at that point just we have to find what? Norm. So let phi 1 equals to what given? First surface x square y square z square equal 9. X square plus y square plus z square minus 9. Just transfer 9 in the left hand side, and that is the phi x or z. Phi, this is equals to 0. This is first surface. And second, phi x square plus y square minus 3 and phi 2 x square plus y square minus 3 minus z. Just take at one side. This is phi 2. Let phi 1 and phi 2 be to surface. Then normal to phi 1 is del phi 1 equals to, that is what? Del phi 1 I sum of I del phi 1 upon del x. In short writing it is what? That means I del phi by del x plus j del phi by del y phi 1 k del phi 1 upon del z. So we can write I del phi 1 by del x with respect to x. So 2x I j plus 2y z plus z 2z k. This is del phi. Normal to this N1 lies N1 equals to this at given point. What is the point? 2 minus 1 2. 2 minus 1 2. So at in place of x, y, z, just find 2 minus 1 2. So what? 4i plus minus 2z plus 4k. This is N1 and normal to phi is n2 del phi 2. So del phi 2 means x square plus y square minus z minus 3. So we can write what? With respect to x, 2x I plus 2y z minus k. Add 2 minus 1 2. So here 4i minus 2z minus k implies n2. This normal to the surface at the point 2 minus 1 2 we have find out. Now since the angle between two surface between two surface is given by the angle between their normals at the intersection point angle between two surface is given by the angle between their normals at the intersection point. Therefore required angle between given surfaces is given by cos theta equals to n1 dot n2 upon n1 modulus of n2 equals to just dot product of these two. What? 4 minus 2 4, 4i minus 2j 4k upon 4i minus 2j 4i minus 2j minus k, 4i minus 2j minus k upon modulus of 4 square minus 2 square plus 4 square modulus of 4 square minus 2 square plus minus 1 square. So this is equals to what? 16, 32, 36, 6, and this 4 16 plus 4 minus 4 upon root 36 root of 21 equals to 16 for 21 4 cancels 14 16 6 16 by 6 root 21. So 2 8 by 3 to root 21. 8 by 3 root 21. 8 by 3 root 21. So this is angle cos theta. So very simple. finding angle between two vectors, that is normal vectors. Okay, so cos theta equal to this. Finally, we can write theta equals to cos inverse 8 by 3 root 21. So this is the angle or answer. Angle between two surfaces. Okay, 8 by 3 root 21 cos inverse of this. Now take another question, find the directional derivative. Now we have to find directional derivative. In the direction of a line PQ where Q is given, directional derivative at P 1 to 3, the direction of the line PQ where Q is given at a point 504, and also calculate magnitude of maximum directional derivative. We know maximum directional derivative is what? Maximum given by grade phi, del phi. What is del phi? So we can find del phi. Now here, first of all, we have to find directional derivative. Our formula for finding directional derivative, we know in a direction, because directional derivative, that means in a particular direction we have to find directional derivative. Okay, so here direction is what? Along the line, in the direction of the line PQ, where P is 1 to 3 and Q is given also 504 point. So we can find the vector PQ, and along this the direction we can find a vector, unit vector a cap. So directional derivative a cap dot grade phi. So first of all we have to find what? Del phi, that is grade phi, and then a cap. Then we can get directional derivative, and maximum directional derivative, that is mod of del phi, we know. Okay, so very simple question it is also. So here given phi equals to, what is the our surface? X square minus y square plus 2z square. Here not phi, here written like f. F equals to x square plus y square minus 2z square. This is given our surface. Now we have to find directional derivative of this along PQ. Directional derivative, so we require what? Directional derivative dd of phi is what? A cap dot del phi. This along phi along is this, that is a cap dot gradient phi. Okay, so here f equals to this, here phi, just if we write in place of phi f, then that will be f, here f. Clear? So here f equal to this, and direction a cap is given by this P 1 2 3 Q 504. Therefore PQ equals to OQ minus OP. So you can find vector give direction, so we require direction, PQ direction. So here OQ means what? 5i plus 0j plus 4k minus I plus 2j plus 3k. So here 4I minus 2j plus k. This is PQ vector. Therefore, our direction unit vector along PQ. Therefore, unit vector along PQ. You can write here. So, unit vector along PQ is given by A cap equals to PQ upon mod of PQ. So 4I minus 2j plus k upon root of 4 square minus 2 square plus 1 square equals to here 21 4I minus 2j plus k upon root 21. Okay, so see here minus 2 OQ minus OP minus 2 to this PQ vector this minus 2j1 to 3 at the point 1 to 3. Clear? This is A cap. Now, our formula will be this for finding directional derivative. So, if for that, A cap is this. Now, what we del F equals to I del y del x plus j del y del y plus k del y del z operator and f x square y square minus 2z square. Okay, so this I del y del x with respect to x, so 2x plus j del y del y with respect to y, 2y plus k with respect to z minus 4z. So this is at P 1, 2, 3. What? P x equal to 1. So 2I, y equals to 2, 4j and 3 minus 12 k. So this is del F. So the directional derivative of F along line PQ is given by what? A cap dot del phi. A cap is this. A cap 4I minus 2j plus k upon root 21 into del phi is this. 2I plus 4j minus 12k. So this is equals to 8 minus 8 and minus 12 by root 21. So here is this? X square minus y square. X square minus y square plus this. This here minus sign. So here minus sign, here plus sign. This is minus sign, plus sign, minus sign, plus sign. So there is a mistake some writing, minus here plus. So this, now we can see that 8 plus 8 plus 12. So this is equals to 28 upon root 21. 8 plus 12 by root 21, 8, 28 to 21. Okay. So this is directional derivative. Directional derivative. Okay. Now we have to also find the maximum. The directional derivative is maximum. We know directional derivative is maximum in since, just you have to write, since, or we know that directional derivative is maximum in the direction of normal to the surface, and it is given by mod del phi. So maximum value of directional derivative. Maximum value of the directional derivative is, what is our, this is 2i minus 14 is this, maximum value of directional derivative is mod del phi equals to mod of 2i minus 4j plus 12k. So its value is what? First find modulus. Okay. So root of 2a square plus minus 4a square plus 12a square. So this is equals to 144. This 20, 164. 164. 164. 164. Root 164. Okay. This is maximum value. This is maximum value. Okay. Because we know the theory about gradient del. Okay, now take question, another question here. Find the constant m and n such that the surface mx square minus 2ny equal to m plus 4x will orthogonal to the surface 4x square y plus z square or ZQ equals to 4 at the point 1 minus 1 2. So here two constants are given in the equation of surface. We have to find that constant, and one surface is orthogonal to other surface. The orthogonal means what? Perpendicularly intersect. That is 90 degree angle between normals. Orthogonal means, orthogonally cut means perpendicular. The normals or tangents are orthogonally cut, orthogonally intersect. So here orthogonal intersection means, orthogonal intersection means normal, angle between their normal is 90 degree. That is normals are perpendicular. That is vector, as a vector, first normal dot second normal is equals to 0. So we can get an equation from there. And also at the point, intersection point is given also. At that point, that is the point will satisfy both equation of surface. So we can get two equation by satisfying any of the surface by the point. So two equation we can get, so we can solve it. So here given first surface, given phi 1, just write transferring on the left hand side. So x square minus 2 nyz, x square minus 2 nyz, x square mx square minus 2 nyz, mx square. Phi 1 equals to mx square minus 2 nyz, okay, minus m plus 4x, minus m plus 4x. This is first surface, and just transferring on the left hand side, and or we can write like this, let. Here we know that phi 1 that is n1 del phi 1, n2 del phi 2, n1 dot l2 equal to 0 because orthogonally cut. So we can get a relation also. So second surface is what? 4x square y plus zq minus 4. 4x square y plus zq minus 4. This on the left hand side, transferring on the left hand side, you can write this 1 minus 1 2 is the point. Okay, so here we have to find constants m and n. We have to find constants m and n. Okay, here we see that since P point, what is the point? 1 minus 1 2, 1 minus 1 2 lies on both surfaces. Therefore, from first surface, first surface will satisfy by this point. So here m 1 square x equal to 1 square minus 2n y equals to minus 1 2n y equals to minus 1 z equals to 2 minus 1 2 minus m plus 4 into 1 is equals to from the first surface, like this, na? So solving this, we can get m minus plus 4 n equals to m plus 4. So here n equals to 1. N equals to 1. Just one constant we got by one relation. Now second, surface 1. Here n1 equals to del phi 1, normal to the surface first, and n2 normal to the surface phi 2. What? Del phi 1 means I del y del x of this. So I 2 mx with respect to x here minus m minus 4. This j plus j with respect to y. Here y is this minus 2nz, 2nz minus 2nz with respect to y, and k minus 2ny with respect to z. Clear? Now I del y del x 8x y plus k z into with respect to y 4x square plus k with respect to z 3z square. At p 1 minus 1 2 n1 equals to and n2 equals to. At this point, so x equal to 1, so 2m minus m minus 4, I m minus 4 plus minus 1 in place of z 2 4 minus 4 z minus 4 nz minus 4 nz, and here y equals to 1 minus 1, so plus 1, so plus 2 n k and 2 x and y minus 1 1 minus 8 I. Okay, here 1 square plus 4z plus 12k, this. Okay, since phi 1 and phi 2 cut orthogonally, therefore orthogonally cut, therefore n1 dot n2 equals to 0, implies n1 m minus 4 into I plus minus 4nz plus 2nk this dot minus 8i plus 4j plus 12k equals to 0. By using this, we can get the relation minus 8, 4j 12k minus 4 plus 12 minus 4 plus 2. N is there, na? So n equals to 1, we can use n equals to 1. Here n equals to 1, we can also use n equals to 1. N equals to 1. Since n equals to 1, so we can write like this. N equals to 1. N equals to 1 get, so n equals to 1 we can use here, n equals to 1. Now, multiply it and solve. So minus 8 m minus 4 minus dot product minus 16 plus 24 is equals to 0. So here 24 minus 16 means 8. M minus 4 equals to minus 8. Minus 8 is there. So implies M equals to 4 plus 1 equals to 5. Thus, M equals to 5, N equals to 1. So this is our answer. M equals to 5, M 5, N 1. Okay. So main thing is what? Here, two surfaces are orthogonally cut. Orthogonally cut means normal are at right angle, cut at right angle, that is perpendicular. N1 dot N2 equals to 0. N1 dot N2 equals to 0. So N1 means what? Del phi 1, del phi 2. So find del phi 1, del phi 2 and add that point. So this and N like point will also lie on the both surface. So first, using first surface, we can get N equals to 1. Okay. Now take another question. Find the directional derivative of x square, y square, z square at the point 1 minus 1 in the direction of the tangent to the curve. In the direction of the tangent, what is tangent? We know tangent line dr. So here curve is given in the parametric form, that is here t. The value of x, y, z depend on t. So tangent vector will be dr by dt. So in that direction we will find unit vectors, that will be a cap, and then directional derivative a cap dot del f. Here function is del phi, function is given phi. So first of all find del phi and then a cap, then we can find value of directional derivative. Okay, so here given function is x square, y square and z square. So directional derivative we have to find the function x square, y square, z square is given. Okay. So here given function is x square, y square, z square. Let phi equals to x square, y square, z square. Then grade phi equals to del phi equals to del of x square y square z square equals to I 2x y square z square plus z 2x square y z square plus k 2x square y square z. This is grade phi. And at the point 1 1 minus 1, so also we find at the point 1 1 minus point, at 1 1 minus 1 1 1 minus 1. So at this value, so z equals to minus 1, so all are 1 to 2i, because 1 1 1 all are 1, z equals to square, so 1, so 2i. Here also all are 1, z is also positive, so 1 2z, z equals to minus 1, so negative, minus k minus 2k minus 2k minus 2k. So 2 minus 2, okay. So what? 2 minus 2. Now this is gradient phi at 1 1 minus 1 implies del phi. We have vector r. Just we know r vector equals to xi yj zk. Here in the given questions are see that x equals to e to the power t, y equals to 2 sin 2t plus 1, z equals to 1 minus cos t at t equals to 0. T equals to 0. If we put t equals to 0 in the given value of x, y, z, then you can get the point like this 1 1 minus 1. That is, point is this. But in parametric form, t is at t equals to 0. That means in at 1 1 minus 1. So here x, y, z in terms of t, that is e to the power t I plus y sin 2t plus 1 z plus 1 minus cos t k. This is the value of r. Now r is function of t. So dr by dt e to the power t I plus 2 cos 2t z plus sin t k, cos t minus sin t minus 1 plus sin t. So this is dr by dt. So the tangent vector at t equals to 0 is dr by dt equals to I plus 2j plus 0k, that is I plus 2j plus 2j at the point t equals to 0. Just t equal to 0 put here, dr by dt is tangent vector. Unit vector along tangent T is A cap equals to vector T upon modulus of T vector I plus 2j upon root of 1 square plus 2 square I plus 2j upon root of 5 I plus 2j upon root of 5. Okay, so A cap is this and del phi is this. Thus, the required directional derivative is given by A cap dot grade phi A cap dot del phi equals to A cap this I plus 2j upon root 5 dot this 2I plus 2j minus 2k. So this is equals to 2 plus 4 plus 0 upon root 5. This is equals to 6 by root 5. This is our solution. Directional derivative. Okay, so 6 by root 5. So very simple. Just you first of all understand what is the basic knowledge about grade phi, del phi, and what is the formula for directional derivatives. Okay. Find the directional derivative of 1 by r in the direction r. Okay, so here see next question. We have to find the directional derivative of 1 by r. Directional derivative of 1 by r. So 1 by r, that is the function of x, y, z. We know r equals to what? Root x square plus y square plus z square. That is function of x, y, z. Okay. So function of x, y, z is 1 by r. So we can find del 1 by r, that is del phi. And in the direction r equal to normal value xi plus yj plus zk. So xi plus yj plus zk. In this direction you can write unit vector r by modulus of vector r. So just take its dot product and then you can get directional derivative. So it is simple to find by using formula A cap dot del phi. Okay. So A cap means in the direction of r, where r equals to xi plus yj plus zk. So here first of all let phi equals to 1 by r. 1 by r means what? 1 upon, we know this, x square plus y square plus z square. That is, we can write what? x square plus y square plus z square or minus half. This is R, function of x, y, z. Then we require what? Del phi. For directional derivative, del phi we require. So del phi. So del phi equals to I del phi by del x plus z del phi by del y plus k del phi by del z, where phi equals to this, where del phi by del x, just find del y del x of x square plus y square plus z square or minus half. So this can be find minus half x square plus y square plus z square power minus 3 by 2, half minus 1, minus 3 by 2 into 2x. So this is equals to what? Minus 1 by 2 x square plus minus x square plus y square plus z square power minus 3 by 2. So you can write minus x r to the power minus 3 by 2, minus x r to the power minus 3 by 2. No, this is r square, r to the power minus 3, since r square equals to x square plus y square plus z square. Clear? So here see that we have to find directional derivative. So now we are given the similarly we can write here also. Similarly, del phi by del y minus y r to the power minus 3, del phi by del z minus z r to the power minus 3. Here this. So therefore del phi can be written as del phi equals to this with ijk. So minus I x j y k z upon r to the power 3. You can write like this, because minus xi minus iy minus zy minus zk upon r to the power 3. This is del phi. Okay. Also r equals to xi plus yj plus zk implies unit vector along R is a cap vector R by modulus of R, xi plus yj plus zk upon root of x square y square z square. And so the directional derivative, hence the required directional derivative is, hence the required directional derivative in this direction is del phi dot a cap. So del phi, this minus xi plus yj plus zk upon r cube. This is vector, this, and xi plus yj plus zk upon root over x square plus y square plus z square. Clear? So this is equals to what? We can write minus of x square plus y square plus z square upon dot product r cube into r. So this is equals to minus r square upon r power 4 is equals to minus 1 upon r square. Minus 1 upon r square. So this is our required directional derivative. Okay? Required directional derivative is this minus 1 upon r square. Okay, here r square equals to x square plus y square plus z square. R square, r cube, r power 4, r square cancel 1 by r square. So this is the solution of this question. Okay. Now there is a very important questions that we have to solve here. This type of here 2 times del operator is applied. Okay. So 2 times, whenever we apply del operator 2 times, so how can we solve it? So see here, we know the square of vector, that means what? The square of vector is equals to vector dot vector. Okay. So here we use that part for proving this identity in the given question. Okay, here the question is prove that is we have to show that here we have to show that del square fr function of r means x square plus y square plus z square root is equals to f double dash r plus 2 upon r f dash r. Okay, we have to prove it. 2 upon r f dash r del square f r. Clear? So for that, see here, we know that square of vector, that is a square equals to a dot a, implies our del operator, vector del operator, this vector square equals to del dot del. That means del square is applied on fr, means del dot del fr, like this. It can be written like this, del dot del fr. So by this basic we can get this relation. Okay, this relation. So here del fr means I del y del x plus j del y del y plus k del y del z of fr. Clear? No. I del y del x of fr. R is also function of x, y, z. Here x square plus y square plus z square equals to r square equals to this. Okay, since this implies del r by del x equals to, you know, x by r, del r by del y equals to y by r, del r by del z equals to z by r. Just we have to use this. We have to use this. Del r by del x, x by r, del r by del y, del y by r, del r by del z, z by r. Here. So see here. Differentiation with respect to, so f dash r del r by del x plus j del y del y means here also f dash r del r by del y, f dash r del r by del z. Now using this value we can write I of f dash r into x by r. Similarly j f dash r y by r, k f dash r z by r. This is the value of del fr. Okay, this. Now del square fr means this, del dot del fr, that is I del by del x plus j del by del y plus k del by del z dot this coefficient of I x f dash r upon r plus j y f dash r upon r plus k z f dash r upon r. Clear? Like this. Now dot product gives what? Del y del x of del y del x of II1. So f dash r product of x by r. Similarly del by del y f dash r y by r plus del by del z upon f dash r z by r. This. Now one by one we have to solve this similar as it. Just first quantity we can solve and put the value here. Okay. So using this del r by del x, x by r, del r by del y, y by r, del r by del z, del z. Now solving this quantity, first part. Okay. So here see first part, del by del x of product of two function, just product of two function, first function, second function, you differentiate as a product. So first time you have double dash r del r by del x. So now we see that del by del x of f dash r into x by r. Clear? First function, second function. This is equals to first function derivative f double dash r del r by del x into x by r. Clear? F double dash r del r by del x by r. Now second function, second part, f dash r as it is, and differentiation of this as division rule with respect to x. So r square, denominator, numerator derivative 1 minus x del r by del x. Now del r by del x equals to x by r. So here we see that f double dash r x by r, this is equals to x by r, plus f dash r, here we see that r square r minus x into x by r. Now it can be solved like this: f double dash r x square by r square plus f dash r, here r square minus x square, minus x square upon r power 3. Now it can be written f double dash r x square by r square plus f dash r y square plus z square upon r cube. Since r square equals to x square plus y square plus z square. Okay, so this is the first part. Same as second part, y. So here y, here z and x. Z, here z, then here x and y. So similarly we can write. So put here value f double dash r x square by r square plus f dash r y square plus z square upon r cube. This first part. Okay, this is first part. Second, for this same, here y, here zx. F double dash r y square upon r square plus f dash r cube z square plus x square, and plus one more value f double dash r z square upon r square plus f dash r x square plus y square upon r cube. Similarly, okay. Now we can collect it. F double dash r, this, So x square plus y square plus z square upon r square. Now plus f dash r comma. Then here also r cube and 2 times all everything. Okay. So here x square plus y square plus z square upon r cube 2 times. Two x square plus 2y square plus 2z square. Clear? Now 2 can be taken common, x square plus z square r square by r cube. So see here, a double dash r square by r square plus a dash r 2r square upon r cube. So finally we get this. F double dash r f double dash r plus 2 by r f dash r. This is the result. F double dash r plus 2 by r f dash r. So you can use this relation and properties just like del r by del s, del r by del y, del r by del z for proving this type of relation. Okay. So del s square means del dot del f r. Clear? So remember this formula. How can we solve del 2 times? Now one more question. For the function phi xy equal to this x by x square plus y square, find the magnitude of the directional derivative along a line making an angle 30 degree with the positive axis of x-axis at 0, 2. So here directional derivative, we have to find the directional derivative. Okay, at 0, 2 on the surface. Okay, here function is given like this, but here x and y are involved, not z. So we can consider for finding direction a cap in 2-dimensional figure. Okay, 30 degree angle with positive direction of x-axis at 0 point. Okay, so first of all we have to find direction and then del phi, gradient phi, directional derivative del phi dot a cap. So a cap is what? Unit vector in the direction of inclination with x-axis with positive direction 30 degree. Unit vector, that is unit length vector. So we have to find the unit vector in the given direction. So for that we will draw the diagram in 2-dimensional figure. So we can see what will be the a cap, unit vector. Okay, so consider the diagram like this for this question. Suppose this is y-axis, this is x-axis, and this is origin. This is y-axis. In this direction, unit vector, and in this direction, I is unit vector. Clear? At 0, 2, that is this. Suppose this is 0, 2. So this direction, in this direction, we can draw parallel line. This is 0, 2. point, and with this 1 modulus, and this is 30 degree angle. Clear? A, this is B, this is B, this is C, suppose. Now, from here, in this direction unit vector, this is unit vector length, vector AB. So, here AB vector equals to AC plus CB equals to AC into I plus CB into J. AC 30 degree. So you can use cos theta base by hypotenuse. So cos 30 degree into I plus sin 30 degree into Z. So root 3 by 2 I plus 1 by 2 Z. This is root 3 by 2 I. This is root 1 by 2 Z. Okay? I got it. This is the diagram. AB vector. Now, so a unit vector along is A cap, vector AB upon modulus of A, root 3 by 2 I plus 1 by 2 J upon root of root 3 by 2 square plus 1 by 2 square. 1 by 4, root 3, 3 by plus 1, 4 by 4, 1. So this is equals to, we can write also same thing, I plus 1 by 2 Z. This is A cap. This is our direction for this question. Here, given that function as phi of xy equals to x upon x square plus y square, two-dimensional. Given that function as this, so we have del of phi equals to I del phi by del x plus z del phi by del y. Here I del phi by del x. It can be written like this: x into 1 upon x square plus y square. Okay. It can be written like this: x dot 1 upon x square plus y square. Phi equals to product of two functions. First function, second function. So partial differentiation. First function 1, second function 1 upon x square plus y square minus first function derivative of this 1 upon x square plus y square into 2x this plus z, partial derivative with respect to y. So x as it is, y means minus 1 upon x square plus y square into 2y. This. So we can write I. Here taking LCM, just 2x square plus y square, x square plus y square. LCM is this. Here x square plus y square minus 2x square, y square minus x square. So y square minus x square upon x square plus y square square plus or minus 2xy upon 2xy minus upon x square plus y square square. Clear? This is del phi. At the point 0, 2, we get del phi equals to 0, x equals to 0, that is it is 0. X equals to 0 and y equals to 2. So here y square y power 4, y square cancel, y square 2 power 4, I by 4. This is at the point this. Now the del phi is a cap. So the required directional derivative. So the required directional derivatives. So the directional derivative along AB is given by a cap dot del phi. Now this is equals to a cap means this root 3 by 2 I plus 1 by 2 z dot del phi I by 4. This is equals to, here we can see that root 3 by 8. Root 3 by 8. So root 3 by 8. So root 3 by 8. Okay, this is our answer. Required directional derivative along AB, this direction, is root 3 by 8. Okay. So by this way you can find solution of different type of questions. Just use basic concept related to gradient, del phi, directional derivative. Okay. Now I will give some questions. These questions are very important. So solve these questions in your copy. Okay. Try to solve more and more questions using different type of books. So do these questions, very important questions. Use the concept as gradient. What is gradient? Gradient is not a vector quantity. Gradient means what? Of scalar point function. Scalar function. That is phi x y z. Gradient is a vector normal to the surface at a point. That is vector. Direction is normal in the direction of normal to the surface. Okay. And its modulus is directional derivative, rate of change of function in the direction of the normal. That is in the normal direction, directional derivative is maximum. Directional derivative is maximum in the direction of normal also. Okay. For finding directional derivative, we use the formula. What formula? Formula is a cap dot del L. phi. Del phi means gradient of scalar valued function. Okay. So do these questions by using concept of gradient of function and directional derivatives and formulas. So very important questions. Solve these questions, okay, in your copy.